So with solution stoichiometry, sometimes when we're reacting an acid with a base, we don't use the word react. Maybe we say we're going to titrate an acid with a base. Titration or titrate is just a term used when you're trying to add enough acid to a base to neutralize it, or add enough base to an acid to neutralize it. And generally what you would do is in a flask, you would have your unknown acid or base, a certain volume of that, and then you would add a few drops of what's called an acid-base indicator, and then you would keep on adding from the burette the known concentration of either the base or the acid until the solution changes color, and you can record how much volume of the base or acid would use to neutralize the unknown component, and then calculate its concentration. So whenever you see the word titrate, it's just a fancy way of saying we're adding enough of the base to completely react with the acid, or we're adding enough acid to completely neutralize or react with the base. And when you're doing problems like this, a very common mistake is students like to use the dilution equation for these types of problems. And I strongly recommend you don't do that. That's not the proper way to solve and what's really a solution stoichiometry problem. So in this question, we ask how many milliliters of a 0.45 molar solution of lithium hydroxide is needed to titrate 50 milliliters of a 0.35 molar solution of carbonic acid. And here it gives us the balanced equation for the acid-base reaction. And so just a few things. What are we looking for? We're looking for the volume of lithium hydroxide. And since we're given concentration, we know that volume equals the moles of lithium hydroxide divided by the concentration of lithium hydroxide. So the way we solve this problem is if we know the moles of lithium hydroxide used, and we know the molarity of lithium hydroxide used, we can calculate the volume. So out of those two things, what we know right off is the molarity of lithium hydroxide. It is 0.45 molar. What we don't know is the moles of lithium hydroxide. That's where we have to use the other information to help us find the moles of lithium hydroxide. And so the other information given to us is the volume and concentration of the acid. And since we have the balanced chemical equation, we can go back and forth between acid and base moles. So what we're going to do is we're going to take the molarity and volume of carbonic acid, convert that to moles of carbonic acid, and then we can get moles of lithium hydroxide. And those are the steps we're going to do. Now we know the molarity of carbonic acid. Its molarity is 0.35. Now the volume we have to convert to liters. That's a very common mistake. People forget to convert to liters. So now to solve for moles, moles equals molarity times volume. And this will tell us the moles of carbonic acid. So now we have the moles of carbonic acid. We need to convert it to moles of lithium hydroxide. So from the balanced chemical equation, we know that 2 moles of lithium hydroxide react with 1 mole of carbonic acid. So our equality or ratio is 2 moles LiOH equals 1 mole H2CO3. So if we know the moles of carbonic acid, we can find the moles of lithium hydroxide. So we set up the little table here to convert. So let me make a bigger table. And it's a 1:2 ratio. So 1 mole of carbonic acid, 2 moles of lithium hydroxide. You need twice as much lithium hydroxide as you do carbonic acid. And so that will tell us the moles of lithium hydroxide. So now we have the moles of lithium hydroxide. We have the molarity of lithium hydroxide. We can find the volume of lithium hydroxide. And remember, this volume is in liters. You notice in the problem it said milliliters. So we have to convert it to milliliters as our final answer. Very important in these, next series of chapters we're going to cover, that you always make sure everything's in the right units that it wants. And so it would take 77.8 milliliters of a 0.45 molar solution of lithium hydroxide to completely neutralize all the moles of acid in 50 milliliters of 0.35 molar carbonic acid solution. So now we're going to be looking at the redox reactions and some of the characteristics with those types of reactions. And so I'm going to, as we go through each reactions, make sure you take good notes, because I'm going to tell you, for example, in a combustion reaction, this particular reactant is always going to be the oxidizing agent. This particular reactant is always going to be the reducing agent. This particular element will always be the species that gets oxidized or species that gets reduced. So make sure you take good notes as we go through, because I want to give you a lot of good tips to help you identify, what's being oxidized and what's being reduced, without actually having to go and look at all the oxidation numbers for some of these types of reactions. Now there are 4 types of redox reactions we're going to discuss. We're going to discuss combustion reactions, synthesis, or sometimes referred to as combination reactions. So you may hear it called synthesis or combination. Brain freeze. I don't know how to spell combination. All right. Decomposition, and we're going to finish up with single displacement. Probably out of all 4 of these, maybe the hardest one to kind of relate to is single displacement, because there we use something called the activity series to help us determine which ones of these will react. So let's look at combustion. Again, these are types of redox reactions that involve the transfer of electrons. So when we say it's redox, there's a change in the oxidation number of one of the species in the chemical equation. So with combustion reaction, the key things you need is you need a fuel and an oxygen gas as reactants. So those are the 2 criteria for reactants for a combustion reaction. You need a fuel and you need oxygen, and you're going to produce oxides of the fuel as products. So if I was to write this as a general equation, fuel plus oxygen gas gives oxides of fuel. And your fuel doesn't necessarily have to be a hydrocarbon. So here, the one I've written on the slide, this is a hydrocarbon fuel, and hydrocarbon means it's made up of hydrogen and carbon elements. So when I say hydrocarbon, this is just one type of fuel, and this is the same fuel that you put in your car when you go get gasoline. It contains the hydrocarbon octane, heptane, and a few other compounds as well. But again, you have to have a fuel for combustion to occur. You have to have oxygen gas. If you don't have oxygen, you can't have combustion. So if you were to try to go on Mars and drive your car, it wouldn't start because there's no oxygen on Mars. And then the products are going to be oxides of the fuel. So for example, here we have a hydrocarbon made up of carbon and hydrogen. We have oxygen as the other reactants. We form the oxide of carbon, which is called carbon dioxide, and the oxide of hydrogen, which is referred to as water or steam. And we produce a lot of energy. Now, for combustion reactions, the fuel is always the reducing agent. So anytime you see a combustion reaction, the fuel is always the reducing agent in that reaction, always. And to be even a little bit more specific, the non-hydrogen atom in the fuel, or non-hydrogen element, I should say, in the fuel is oxidized. So you have a combustion reaction, it has some fuel. The fuel is always the reducing agent. The non-hydrogen element in the fuel is always oxidized. So if we're looking at hydrocarbons, that means the carbon is always oxidized in a combustion reaction if we're using a hydrocarbon. And the hydrocarbon itself is always the reducing agent. Now, if you have something that is oxidized, you have to have something that is reduced. And so for oxygen gas, O2, O2 is always the oxidizing agent. And that's because oxygen is always reduced. Again, this is for a combustion reaction. So anytime you see a combustion reaction, you should automatically know, okay, fuel is going to be the reducing agent. Oxygen is going to be the oxidizing agent. And we know that the non-hydrogen component in the fuel is going to be oxidized, and oxygen is always going to be reduced. So the fuel, the non-hydrogen element is always going to give up electrons. Oxygen is always going to gain electrons. And as I said, these are extremely exothermic, meaning they give off a lot of heat. So if you use an internal combustion car, when you're driving your car, it produces heat because the combustion reaction produces heat. And so that's why you have to have something to remove the heat from the combustion chain. Secondly, combustion reactions produce a lot of gas. So when you're driving your car, that's why you have to have exhaust if you're using an internal combustion engine, because it has to have a way of evacuating the gas from the combustion chain. Now, this is all because we use a combustion reaction to drive our car. Now, some examples. Here we have the combustion of propane. So if I was to ask what elements is oxidized, it would be the non-hydrogen element in the fuel. So the fuel here is propane. So carbon would be oxidized. Oxygen would be reduced. And propane would be the reducing agent. And the reducing agent contains the species that is oxidized. and oxygen is the oxidizing agent. So again, the agent is the reactant or product that contains the species that is oxidized or reduced. So agent has to be a reactant. It cannot be a product. And an agent is the actual reactant that contains the species that is reduced or the species that is oxidized. We look at another example. Here we have hexane plus O2 gives us CO2 and steam. Again, the non-hydrogen component in the fuel is oxidized, so carbon is oxidized. So that means C6H14 is the reducing agent. Oxygen is reduced. It is the O2 is the oxidizing agent. And you may say, well, how do I know that you're telling me the truth? And okay, we can take a stab at it. So just to show you that carbon is oxidized and oxygen is reduced, and you might be a little shocked here, but we'll go ahead. So again, carbon, hydrogen's attached to a nonmetal. It has a +1 charge. And so there are 3 carbon times X plus 8 has to equal 0. And so here carbon is a -8/3. All right. And yes, carbon is strange like that. It can have weird oxidation numbers. The fact is, you have to remember hydrogen is a +1. Here O2 is by itself. It's a 0. Now in CO2, oxygen is -2. Carbon is +4. And then in H2O, hydrogen is +1 because it's attached to a nonmetal. Oxygen -2. So now you see carbon goes from a -8/3 to +4. So carbon is oxidized. Oxygen goes from 0 to -2. Oxygen is reduced. And this is always the case when you're dealing with combustion reactions. One last example. Here we have a different fuel. Now we have a nitrogen-based fuel. But again, the non-hydrogen component is oxidized. So nitrogen is oxidized, and so N2H4 is the reducing agent. O2 is the oxygen in O2 is still reduced, so oxygen or O2 is still the oxidizing agent. Again, the agent is always going to be a reactant. It's never a product. So if you have a series of choices and you see some of those choices are products, you should disregard those choices because agents are the only reactants. So this is one type of redox reaction. I've given you important tips on identifying the oxidation or the oxidizing, reducing species, and also the oxidizing and reducing agent. Next type is synthesis, and with synthesis reaction, or sometimes called combination, depends on what book you read, but it's the same thing. So you may see it synthesis in older textbooks and newer textbooks. They call it combination reaction. Either one is fine. And so the key characteristics of this is you have multiple reactants and you produce one product. And so there are many different combinations that can give you one product. Some of them are redox, some of them are not redox. So some examples are we can have multiple elements give us a compound. And since we have elements on one side and compound on the other, this is redox in addition to being synthesis. Now, if your elements, and these are just some general tips, if an element is a non-metal, typically it's reduced. And if it's a metal, generally oxidized. And the way I said, well, the reason I say generally is because there's probably some weird exception out there. Well, someone will find on Google, which is kind of contradicts this. That's why I say generally, if you have two elements, one is a metal, one is a non-metal, the non-metal generally is reduced, the metal is generally oxidized, so that tells you the non-metal is the oxidizing agent and the metal reducing agent. This is one way you can get a synthesis reaction. Another way is you have a compound plus element gives you compound. And this is redox. Now I can't give you any tips on this type of combination because it depends on what the compound is and what the element is to determine what's being oxidized, what's being reduced. So on this type of combination, you would have to look at each oxidation number and see what the change in the oxidation number is. And then the last combination is when you have multiple compounds, give one compound. And this is generally not redox. So there's going to be no change in the oxidation numbers of your species in these compounds. Again, generally means most of the time it's not redox. If you're concerned that it may be redox, you just monitor the oxidation numbers and you can determine whether it's redox or not. So here, for example, we have the synthesis of glucose. So we start with the elements, carbon, oxygen, and hydrogen. We get C6H12O6. So this is a synthesis, and since we go from elements to compound, it's also redox. Because remember, species in their natural form all have a zero charge. And so all of these take part in the redox process because they're all elements and they all get put into compounds. Now, we look at the next example. We have calcium plus oxygen gives us calcium oxide. Again, we have elements. If it goes into a compound, it becomes redox. Or excuse me, okay, becomes a non-zero number. And so here we have a metal and a non-metal. So the metal is going to be oxidized. The non-metal is going to be reduced. So calcium is the reducing agent. Oxygen is the oxidizing agent. And then lastly, we have SO2 plus H2O gives us H2SO3. Here we have two compounds, gives us one compound. Since they're both compounds, there's no change in the oxidation number. And if you wanted to confirm this, oxygen here is a -2 because it's oxygen here is a -2 and oxygen here is a -2. The sulfur is a +4. Hydrogen's a +1. Here hydrogen's a +1 and sulfur is a +4. So there's no change in oxidation numbers. Therefore, it's not a redox reaction. Again, this is synthesis combination. We're looking for multiple reactants. Gives only one product. Next, we have a decomposition. So decomposition is the opposite of synthesis. So here we have the characteristic one reactant gives multiple products. And so again, what we're looking for is we have one reactant gives multiple products. And so there are different ways the compound can decompose. So just like with synthesis, we can have a compound that decomposes into elements. And so this is redox. And again, if it's decomposes into non-metal and metal, non-metal is generally going to be, oh, this is backwards. So yeah, this would be backwards to synthesis. So if it's a metal as one of the elements, it's going to be reduced, and a non-metal as one of the elements, it'll be oxidized because you're going backwards here. So that's a good tip for decomposition reactions. Now another type is a compound decomposes in a compound plus elements. And then of course, this is redox. But when you have a compound decompose into compound plus compound, this is generally not redox. And again, for compounds, usually there's not a change in oxidation numbers. So here we have the decomposition of pentane into carbon and hydrogen. So typically, since there's a metal and a non-metal, the metal will be, oops, I got that backwards. So the metal, wait, yes. Oh no, that's general, yeah. So here, I guess there's no metal, so hydrogen is a +1, carbon is a -2. So carbon goes to 0, hydrogen goes to 0. So here hydrogen is reduced and oxygen, or excuse me, carbon is oxidized. And in this example, C5H10 is both the oxidizing and the reducing agent because it contains both the species that is oxidized and reduced. Here we have silver nitrate. So silver nitrate decomposes into silver, oxygen, and nitrogen. And so since we're going from a compound to elements, redox has occurred. And then lastly, we have the decomposition of calcium carbonate. It decomposes into calcium oxide and CO2. Since it decomposes into compounds, this is synthesis, but it is not redox because there's no change in the oxidation numbers. So the last set of reactions, the redox reactions we're going to discuss is single replacement. And here it's similar to double displacement, but the key difference between single replacement and double displacement is, for double displacement, you have two compounds as reactants and products. For single replacements, you have an element plus a compound gives an element plus a compound. So you notice here, for single replacement, there's an element on both sides of the reaction. And for double displacement, it would be compounds for the entire reaction. So that's the difference between single replacement and double displacement. And so what happens is the elements replaces one of the species from the compound. Now, if the element is a metal, then it would replace the cation. So let me write that here. So if your element is a metal, it's going to replace the cation, and the metal is going to be oxidized. Now, if your element is a non-metal, or usually a halogen, and this is the only case, so it would be a halogen, then it replaces the anion in the compound. And the non-metal is reduced. And so if you know that the element is a metal, if the element is going to be oxidized, that means the element is the reducing agent. The compound has to be the oxidizing agent. Now, if your element is a non-metal, say a halogen, and we know that the non-metal is reduced, that means the element is an oxidizing agent, the compound is a reducing agent. So determining whether the element is a metal or non-metal will help you understand whether the element is going to be the oxidizing or reducing agent. And so here we have magnesium plus water gives us magnesium hydroxide and H2. And so what happens is magnesium is a metal, is going to displace the cation, or the one with the positive charge, so it displaces hydrogen, and we get magnesium hydroxide. Now, since magnesium is a metal, magnesium is oxidized, so it's the reducing agent. Hydrogen is reduced, so H2O, the oxidizing agent. So the fact that the element is a metal means that the element is going to be the reducing agent. The compound will be the oxidizing agent. Now, when you put a metal and acid together, and we'll show some examples of this, but you produce a gas, which is hydrogen. So there are metals that will displace hydrogen from an acid, and you get the H2 as a product. So here we have aluminum plus copper chloride gives us aluminum chloride and copper. And so again, aluminum is a metal. It's going to be the reducing agent. And copper 2 chloride is going to be the oxidizing agent, because the metal is going to displace the copper. So the aluminum is going to be oxidized, the copper is going to be reduced. And again, the way we know that aluminum is going to displace the copper is based on something called the activity series, which I'll show in just a moment. But the more active element wants to replace the less active element. So here we have nickel and HCl. So we have a metal. The metal is going to be the reducing agent. HCl is going to be the oxidizing agent. And so again, nickel is more active than hydrogen. It displaces the hydrogen, and we get nickel 2 chloride and H2. So anytime you have a very active metal with an acid, it will displace hydrogen from the acid. Now we have a halogen, and remember now if the element is a nonmetal, it's going to displace the anion. And so since the element is a nonmetal, the nonmetal is going to be reduced, so this would be the oxidizing agent. And this would be the reducing agent. And so for halogens, the more active halogen is higher up on group 17. So fluorine is the most active halogen, iodine is the least active halogen. And then lastly, we have nickel plus KCl. Now this is no reaction because potassium is more active than nickel, so no reaction will occur. And so now the way we know that some elements will react, some won't, is based on the activity series. And the activity series is showing you which elements are more active than others. Now you don't have to memorize this table, you just have to know how to utilize the table to know which reactions will occur and which ones will not. And so we looked at, for example, aluminum plus copper chloride, and we had some products. And so the reason that this reaction occurs is if we find aluminum, it's located here. We find copper, it's located here. So since aluminum is above copper, it will displace the copper. Another example we had was nickel plus potassium chloride, no reaction. And so we go here, we find nickel. Nickel is right here. Potassium is above nickel. So therefore, no reaction would occur because the more active element is already paired up. We had one with HCl, so say zinc plus HCl gives products. So zinc is here, hydrogen is here. So since zinc is above hydrogen, it will react with the acid and displace the hydrogen. However, if we tried silver plus HCl, no reaction would occur because silver is below hydrogen on the activity series. So silver is not active enough to displace hydrogen. Now, the greater the difference, the two elements, the more vigorous the reaction. So for example, if I take lithium plus HCl, now lithium is here, hydrogen is here. So a reaction involving lithium and hydrochloric acid would be more vigorous than a reaction involving zinc and hydrochloric acid, because the further apart two elements are, the more vigorous the reaction. And so this is how you use activity series to determine which reactants will react and which reactants will not react.